All right, this next section is going to be a combination of weak acids and weak bases, with some strong acids, strong bases thrown in for good measure. It's all about salt solutions. When you dissolve a salt and it breaks up into two parts, it's going to react with the water in the division such that the positive ion is going to dissolve with or connect or bond with the negative ion, and the negative, which is the hydroxide, and the negative ion of the salt is going to combine with the positive part of the water, which is the hydrogen. And when we say salt, we mean an ionic compound, which means any metal in a compound, or ammonium, NH4 positive, in a compound as a positive ion, is considered an ionic compound. So what we're going to do is we're going to take the salt, which has been created from an acid-base reaction in the first place, add water to it and force it to the opposite direction, the reverse reaction to get to that point. And then we're going to examine what we have. And what is going to occur here is you're going to get an acid and a base of different strengths, maybe. Now, if it's like sodium chloride when dissolved in water gives you sodium hydroxide and hydrochloric acid, both of which are strong acids and bases, and therefore create a neutral solution. There'll be no, the pH of that solution will be 7. There'll be no excess acidic or basic ions. Most salts will not do that. Just a handful will do that. So we're going to start off looking at that with a couple of practice problems. On page 763, problem number 51, we're going to dissolve iron 3 nitrate in water. Now again, when we react with water, we don't think of it as H2O, we think of it as hydrogen hydroxide. And all the exercises is going to be pertaining to that, as you'll see. So we need to put the charges above. Iron's a transition metal, we don't know what it is, so we look at the polyatomic ion charge of nitrate, which is -1, and we have 3 of them. Therefore, the charge of iron is +3. And we already know that hydrogen is +1 and hydroxide is -1. So the double displacement reaction that occurs is going to have Fe with OH and H with NO3. Now this 3 is ignored because it's only there because of the +3 charge of hydrogen. We're just going to put that on there, and then we'll look at the charges from up here down there, like we always did with the double displacement reaction. Iron is +3, hydroxide is -1, hydrogen is +1, nitrate is -1. And I'm not going to worry about the phases at this point. We're just going to try to figure out what's going on in the relationship between this base and this acid that we've created. We are going to balance the charges of the ions, however. This does not add up to 0. So that means we put a parenthesis around that, and we need ×3 for this in order to balance that out. So we need 3 hydroxides. This is already balanced, so we don't need to do anything with it. And that's as far as we really need to go with this, as far as dealing with the equation. Now, what we're going to do is we're going to examine each acid, each base, and determine if we have a weak acid or a weak base. And then we'll go from there. So Fe parenthesis OH parenthesis 3, or iron 3 hydroxide, is that on your list of strong bases rather? And the answer is no. Only the group 1 and group 2, half the group 2 metals are. So this is considered a weak base, which I will abbreviate as WB. Weak base. Is HNO3 on the list of strong acids? The answer to that is yes. This is a strong acid. So if your solution has a mixture of strong acid and weak base, you can pretty much surmise that the dominant compound in this pair will be the strong acid. So the fact that that is the dominant of the two means that this solution is going to be acidic. Okay? So when you dissolve this in water, this is going to be acidic. I used to live in a mining town in Minnesota when I was a young teenager. They had a gigantic mine north of town that dealt with taconite. And it was an open mining system, which means they didn't go underground and dig. They just blew the crap out of everything with dynamite and then took out all these huge chunks of low-grade iron ore called taconite and then shipped it off to Duluth, Minnesota. After a while, especially those that were idle, the mines got filled up with water. Well, what's exposed to the conditions are iron compounds. And iron compounds in water, as you can see, gives you an acidic solution. And so you had developed a somewhat acidic water reservoir that nothing could live in. So the EPA, the Environmental Protection Agency, said that any abandoned mine must be treated so that so that living creatures could live in it. So they had to deacidify it by adding some kind of base to it, which we'll get into later on. All right, here's another example right here. Again, we need to go through the charges. This is ammonium is on your polyatomic iron chart as +1. This is perchlorate, ClO4 is perchlorate, so that's -1. And of course, we know this is +1, this is -1. So the hydrogen and the ammonium are going to switch places, and that's going to give us HClO4 plus NH4OH. Alright? Is HCl4 is an acid at the end of the hydrogen here. Is that one of the 7 strong acids? Yes, it is. So this is a strong acid. Ammonium hydroxide, is that one of the strong bases? No, it's not. So this is a weak base. So again, just like before, this is the dominant one. And so part B is acidic. So that's how we do that. There's 4 parts of that you're going to be doing for your practice problems. We're going to do the same thing with number 53, only instead of using formulas, we're going to be using words. That means we're going to have to use the charts on page 727 for acids and 736 for bases, like we did in the previous assignments. Ammonium, you see IM here and here. This is saying that this is the positive ion form of the compound from which it came. What compound? This is ammonia. And this is aniline. But we've replaced the UM in each case. Sometimes it's the whole IUM, but the UM, or the NE with UM and the A with UM, which tell us that this is a positive ion. So we go to the charts and we find ammonia or ammonium, and ammonium is NH4 positive, and acetate is this is from the acetic acid that we got acetate from. Remember, we change bases to acids by dropping the ATE and putting it in acid. So this is a weak acid from whence it came. So the acetic acid is CH3COOH, but because this is acetate and not acetic acid, which is its root, that means it's lost its hydrogen and has a negative charge. I'll do that for both. Now, we come back here to aniline, which is from aniline. Aniline is C6H5NH2. or NH rather, but because of the positive ion. Remember the difference between an acid and a base is one proton. So, and that's what we're doing here. We're adding a proton to ammonia. Ammonia is originally NH3, and then we add a hydrogen to that. Aniline is C6H5NH plus a hydrogen to make an acidic ion, an acid. So this is going to become C6H5NH2. Okay? So the compound that we're actually looking at here is NH4CH3COO. So these are their roots right here. Okay? And the roots for that came from ammonia, NH3, and acetic acid, CH3COOH. Okay? So, what we need to do then is to find their Kas and Kbs based upon that. Now, I'm going to tell you that we're going to be looking at the Kb for ammonia, and we find that that is 1.8 times 10 to the negative fifth. And the acetic acid is 1.7 is the Ka, which we find on page 727, 1.7 times 10 to the negative fifth. So we have two weak substances. So what we do is we base this upon the base of the compounds from which they came. We look at the Kb, which is slightly bigger than Ka. So this is stronger. The base of that is stronger. So this is going to be basic. Over here, if we take a look at acetic acid again, we said that the Ka of acetic acid is 1.7 times 10 to the negative fifth. And the Kb for this, well, we have to find aniline on page 736. And if you look for it, you see that it's going to be 4.2 times 10 to the negative 10. Well, in this case, this is a much lower number than this right here, because negative 10 is way smaller than 10 to the negative 5. So this is the dominant one. So that makes this acidic.